Here are two examples of integrals involving trig functions. The two examples in this video will involve integrals that involve sine and cosine, various powers of them. Let's start by finding the integral of sine to the fifth of x dx. With most integrals involving powers of sines and cosines, you'll want to figure out which of these trig functions, if either, has an odd power. In this case, there's only a sine function, and it does have an odd power. Usually, with these problems, you'll want to solve the problem by doing a u substitution. So we'll choose a u, and we'll determine our du. And usually, the u will either be sine or cosine. Now, you might think that the good choice for u here is the sine of x, because that is the function that is inside another function. That's the function that is being raised to the fifth power. The problem is that our du here would be cosine of x times dx, and there is no cosine showing up in the original integrand. So we will not be able to replace our dx with our du because there's no cosine of x that should be replaced along with the dx. This is not going to work. Instead, let's allow our du to be sine of x. We may have to correct this in a moment. If our du is sine of x, then that means that our u can be cosine of x, but the derivative of cosine x is negative sine x dx. So we'll just add that negative to this. Now, of course, we can divide by the negative here and say that negative du equals sine x dx. So let's take our integral here. This equals the integral of, let's just split off one of those sine x's. So we have sine to the fourth of x times sine of x dx. Now, this part, our sine of x dx, can be replaced with du. And usually, the best thing to do in these kinds of problems is figure out what your du is first. That is the most difficult part to get right. So get that part right, and the rest will follow. Now, the problem we have is that we have the rest of our integrand here involves a sine function, but our u is cosine of x, not sine of x. So what can we do? Well, here's where we need to go back and look at our trigonometric identities and see if we can rewrite this expression involving sine of x as something involving cosine of x instead. In particular, we have an even power on the sine of x. It's sine to the fourth x. That means that we can use one of the Pythagorean identities. Let's look at those. Here are our three Pythagorean identities. They all come from the unit circle. And if you find an angle theta anywhere in the unit circle, you can make a right triangle with the hypotenuse coming from the origin out to the circle. The hypotenuse is 1, and the height of that triangle will always be sine of theta, and the base will be cosine of theta. So we can use the Pythagorean theorem and write sine squared theta plus cosine squared theta equals 1. You can get the other two identities by taking the first equation and either dividing by cosine squared theta or dividing by sine squared theta. Each of those choices will give you one of these other two identities. Let's use the first one this time. Let's go back to our problem. So we know that sine squared of x in this case plus cosine squared of x equals 1. In particular, that means that sine squared of x equals 1 minus cosine squared of x. So let's work this out. This equals the integral of, well, sine to the fourth x, that's really sine squared of x squared, isn't it? So we can replace sine squared x with 1 minus cosine squared x squared times sine x dx. Now we're ready to go. because now we have our du right here. Well, it's really negative du, so there we go. But again, we don't need to worry too much about the constant multiples here. They'll sort themselves out. And everything else involves our u. That's u squared right there. So we're ready to go. We can do our substitution here. This equals the integral of 1 minus u squared times negative du. I'll put the du here and the negative in front of the integral. Let's give ourselves a little bit more room to work here. I'll bring this right around here. In order to integrate this expression, we're going to need to start by squaring that 1 minus u squared. That will give us 1 minus 2u squared plus u to the fourth times du. And this is now an easy integral to solve. This is negative u minus u to the third times 2 over 3 plus u to the fifth over 5, plus a constant, of course. And we can distribute that minus sign. And also, let's fill in what our u is. We determined that our u was cosine of x, so we have negative cosine of x minus a negative, that's plus 2/3 cosine cubed of x. And we'll come down here, minus a positive, that is negative cosine to the fifth of x over 5 plus a constant. That is our final answer right here. Expect these kinds of problems to come out with fairly long and complicated looking solutions. There are usually not neat and tidy solutions in these kinds of problems, and that's okay. This is the kind of solution we should expect. Now let's do another example. Let's find the integral of cosine to the fourth of x dx. Now, you might consider using a u substitution this time again. After all, in the previous problem, we had sine to the fifth of x dx, and we found that if we set our du equal to sine x, or negative sine x, then our u could be cosine x, and we were able to convert the remaining trig functions to be in terms of our u. This time, that's not going to work. Let's see what happens if we set our du to be cosine of x. Then our u can be sine x. Of course, don't forget the dx here for our du. No negatives here because the derivative of sine x is positive cosine x, so we're all set. This integral is equal to cosine cubed x times cosine of x dx. Here again is our du. And if we could find a way to convert that cosine cubed of x into something involving the sine, we'd be all set. The trouble is that our trigonometric identity here, our Pythagorean identity, says that cosine squared of x equals 1 minus sine squared of x. It doesn't tell us what cosine cubed of x is. Now, you could take the square root of both of these and then cube the result. In other words, cosine cubed of x is equal to 1 minus sine squared x to the 3/2. But that is not going to be fun to integrate even after we do the u substitution. This is going to be very, very difficult to solve. And the u substitution is not actually going to help us in this case. So this is not going to work. In general, this simple u substitution that worked in our last problem only worked because the power on the sign in that case was odd. That meant that you could split off one of the sine x's to go with your dx and make that your du. And what was left over was an even power on the sine x's, and you could use that Pythagorean identity without having to take any square roots. This time we're starting with an even power on the cosine of x. If we split off one of those cosines to be our du, what the remaining cosines is cosine cubed, and we will not be able to use this Pythagorean identity without a lot of square roots that make everything much too hard to solve. So let's back up and try something different. Let's take a look at another set of trigonometric identities that we can use. When you find that you have an integrand that's a product of sines and cosines with an even power on the sines and cosines, like in our case, we have cosine to the fourth times sine to the 0 power, technically, so that's also even. What's very useful are these two half-angle formulas right here, sometimes called the power-reducing formulas. These actually come from the double angle formulas for cosine of 2 theta and the Pythagorean identity that we have. So in particular, sine squared of theta is equal to 1/2 minus 1/2 cosine of 2 theta. This means whatever theta is, whatever the argument of your trig function is, you will replace it with an expression that has a lower power, but the argument of the trig function is doubled. And cosine of 2 theta equals 1/2 plus 1/2 cosine of 2 theta. In this case, we'll want to use the second one right here. So let's copy this down. We know that cosine squared of x in this case equals 1/2 plus 1/2 cosine of 2x. So let's use that. We don't have cosine squared in our integral. We have cosine to the fourth, but that's easy enough to handle. Cosine to the fourth of x is actually cosine squared of x squared times dx. Now in this case, I think I'd like to rewrite my half-angle formula before we start. I'd like to factor out that 1/2. I think it's going to help us to make things a little easier to work with here. So this is 1/2 times 1 plus cosine of 2x. Now let's fill this in. Let's replace in our integrand, let's replace the cosine squared x with that formula from the half-angle formula. So we'll have 1/2 times 1 plus cosine of 2x squared. A lot of parentheses here. Watch out for that. And of course, don't forget your dx. Now we'll just need to do some algebra and simplify this expression. Since we are multiplying two things within that squared here, we can square the 1/2 and also square this binomial sort of expression here. So 1/2 squared is 1/4. And now we'll take 1 plus cosine of 2x squared. So that's the square of the first term, which is 1, plus twice the product of the two terms, so 2 times 1 times cosine of 2x, plus the last term squared, that's cosine squared of 2x. And of course, we'll close that parenthesis there and put our dx at the end. We can pull that 1/4 out in front of the integral if you want to. You don't have to. You might even choose to multiply it in instead. It's up to you. Now we still have this 1 plus 2 cosine of 2x plus, now we have a problem here. We still have a square on our cosine. We'll be able to integrate the 1. That's easy. We can integrate the 2 cosine of 2x. That's also pretty easy. What we don't know how to do is cosine squared of 2x. What do? Let's use that half-angle formula again. So the cosine squared of whatever angle is equal to 1/2 plus 1/2 the cosine of twice the angle. Whatever the angle is, it's going to be doubled now. If our angle started off as 2x, our angle is now twice as big. It's going to be 4x. And we have this whole expression times dx. Now let's give ourselves a little bit more room and work this out. This looks more complicated than it was, but it's really not. What I might do, just to keep things organized, I don't like having all of these different coefficients in all these different terms and also multiplying the entire integral by this 1/4 here. I think that that's going to make things very confusing later on. I think I'd like to actually multiply that 1/4 in so that I have all my coefficients put together. This equals the integral of, well, first, we've got two constants, don't we? We've got the 1 plus the 1/2 here. That's 3 halves. So I'm going to multiply the 1/4 times 3 halves, and I'll simplify that later. Plus, we've got 2 cosine 2x, but 1/4 of that is going to be 1/2 cosine of 2x. And finally, we've got 1/4 of 1/2 cosine 4x. That's 1/8 cosine of 4x. All this is times dx. Maybe now's a good time to cross this out and call that 3/8 instead. Now we're ready to go. Now we just have a sum of 3 terms. Each of them's got some kind of a coefficient, and they're all pretty easy to integrate. So let's actually do the integral now. Let's find the antiderivative. So 3/8 is a constant. The antiderivative of a constant is going to be 3/8 x plus 1/2 cosine of 2x. Well, if we take the antiderivative, it's going to be sine of 2x. But you need to use a u substitution here, technically. Your u would be 2x. And if you do that process, what you'll find is that you're actually going to divide by 2. So you're actually going to have a 1/2 here. Plus, we've got 1/8. Again, the antiderivative of cosine of something is going to be sine of that thing, sine of 4x. But again, we'll have to do a new u substitution here, where the u is 4x. And if you actually work that out, you'll see that you're going to divide by 4. So we'll say times 1/4. And this is also an indefinite integral, so I need to add a constant, plus c. We're almost done. This is technically the correct answer. I just like to simplify a little bit. Let's clean it all up. So we've got 3/8 x plus 1/2 times 1/2, that's 1/4 sine of 2x, plus 1/8 times 1/4, which is 1/32 sine of 4x, plus our constant. This is our solution. So the trick here is, if you are integrating a function that's a product of sines and cosines, if the power on either the sine or the cosine or both is odd, you'll be able to split off one of those sine x's or one of those cosine x's to be a du, and you'll be able to do a u substitution using the Pythagorean identity. If the power on both the sine and the cosine is both even, then you'll need to use the half angle formulas, which will allow you to bring down your power at the cost of doubling the angle.